Hi everybody, here I am. So in this video and in this section we are going to continue talking about confidence intervals for the population mean. So we just had a couple of videos where we did all these computations and examples in which the population standard deviation was known ahead of time. Okay, and I said it was, that might seem a little strange because why would sigma be known when mu is unknown? But I said to go with it, and now we're going to say, well, what does happen if it is unknown? Can we proceed? And the answer is yes, if certain conditions are right. Okay, and what are those conditions? So suppose if we wish to construct a C confidence interval for mu using a sample size of n, but sigma is unknown. Question, can we still proceed? The answer is yes, as long as n is greater than or equal to 30, or the population is normally distributed. Okay, so in other words, as long as the conditions for the central limit theorem are still hold. Okay, now if that's the case, then we can just replace the population standard deviation with the sample standard deviation S. Okay, and we know how to compute that on our calculators if we need to compute it. Then we replace the standard normal distribution with a different distribution. Okay, something called a t-distribution. And a t-distribution, if you look at the graph of it, it almost looks the same as a normal distribution, but it's the curve, the tails are a little thicker on the ends. It's still symmetric and bell-shaped, centered at 0. But actually we have not just one t-distribution, there's like a whole bunch of t-distributions. And we have a different t-distribution for each number between 0 and 30, or 1 and 30. And we talk about something called the degrees of freedom for a t-distribution. So every t-distribution has its own number of degrees of freedom, and we use the one with n-1 degrees of freedom. Now, you don't have to actually look this up on your calculator. What you can do is actually look it up. The easiest way is really to look it up on a table here, which is, it comes with your book. If you have a physical book, it's in the back of the book. Otherwise, you can print this out easily enough directly from while you're doing your homework. Okay. Or from your electronic book. But basically, it's the same idea. If we want an interval with confidence level C, we basically we're replacing Z sub C with T sub C, and T sub C is basically the boundary of this region where we have the area of the middle region is C, and T sub C is the value of the right boundary. And we look at that up at our table, and then we compute the margin of error, just as we did before. We just replaced Z sub C with T sub C, and we've replaced sigma with S. And then it's just business as usual. Okay. Now let me just give you a couple examples of how this would work and how we use our table. So in this case, let's say so we want C to be 0.90. All right. So the sample size is 10. So we do need to know what the sample size is ahead of time. So that means the degrees of freedom is 9. The number of degrees of freedom is 9, right? And this is the sample mean that we've computed, and this is the sample standard deviation that we've computed. So we go to our table, and since we're looking at levels of confidence, we want this, and we want 0.90. That's our C. Okay, and then we go down and look at we said the level of confidence was 9, so we look at the degrees of freedom is 9, so we look at 9, and under the column for 0.90, and we see that our critical value is 1.833. Okay, so that tells us that T sub C is 1.8. What did we say it was? 3. Okay. And then we just compute what the margin of error is, it will be 1.833 times S divided by the square root of n, which is 10. Okay? And when we compute that, this turns out to be approximately 1.796, which again, because our number of decimal places is 1 for the sample mean, we're just going to round this to 1 decimal place. So this is 1.8. So that's our margin of error. And then our confidence interval would be 32.6 plus 1.8, 32.6 minus 1.8. And so that gives us a confidence interval of 30.8, comma 34.4. Okay. All right, let's do one more example. Let's say in this case, if the confidence level is 0.95, the sample size is 18, that means the degrees of freedom would be 17. So we look at our table. Here's 0.95 up here. By the way, we're going to ignore these one tail and two tails for now. We'll use that. We don't use that until we use hypothesis testing. But here's our column for C equals 0.95, and we want 17, and we see that's right here is 2.110. So T sub C would be 2.110. Then E sub C is 2.110. In this case, S is 2.53 divided by the square root of 18, which is approximately 1.26. We might as well just round off to 2 decimal places again because that's what we have here. Take 50.13 plus 1.26. 50.13 minus 1.26, and then the interval turns out to be 48.87, I think, and 51.34. Okay. That's this one. This is the first value, and then this is the second value. Okay. All right. So it's not too hard if we make those substitutions. The hardest thing about this is just knowing which formula to use. You have to read very carefully, because sometimes the problem will just give you here's what sigma is and here's what S is. But sometimes they'll say they won't give you those symbols. Sometimes they'll just say the population standard deviation is whatever, or the sample standard deviation is whatever. So you have to read very carefully, especially when they'll say something like a sample of size n has mean 13.45 and standard deviation 2.3. And you have to recognize that that standard deviation they're talking about is associated with the sample. So that is S. That's not sigma. You only want to, you only want to use the formula for sigma if they specifically give you the word sigma, or the symbol sigma, or you see the word population standard deviation. Okay, that's what you want to read for if you're going to use sigma. Otherwise, you're going to have to use S, and they use S in the T distribution. So read the problem very carefully, and you'll be fine. Thanks. See you next time.